house right now. If you want to chat and say where you're from and put it into the comments underneath, that would be great, much appreciated, and very glad that I've got your company this evening. Good, you can hear me, that's great. So why do we care? Well, we care because the IB care. The IB care. Why do the IB care? Because it's a threat to humanity. We need our ozone. We need our ozone in the right place. Okay. You may be familiar with the places above your head. The troposphere, where the aeroplanes fly, it goes up to about 12 to 18k. The stratosphere, 11 to 50. You can read the rest. The actual numbers I wouldn't worry about at all. They are arbitrary. They are pretty much different on each website you look at. I tried to use NASA as much as possible. They seem to be quite consistent, peer-reviewed, and hopefully the IB is never going to ask, what range is the thermosphere going to be in? I'm sure that will never be the case. So, where ozone resides determines whether it will protect you or it will harm you. Okay, to protect you, we want it up at the top. We want it up in the stratosphere. We want it here in the stratosphere. We don't want it in the troposphere. And one of the teachers from the IB group was commenting that his job was to Charles Piety, I think his name is. That's him. Was commenting his job was monitoring the ozone levels in New York, and he obviously enjoyed himself so much. He's now pursuing a lifetime career in chemistry. Victoria Stazluka, sorry for my pronunciation. Yes, this will be saved. I will share it in the IB Chemistry Teacher Facebook group, and it'll be on my C. Okay. So most ozone is in the stratosphere, quite high up where it should be, and it does shield us from the high energy, very dangerous UVB radiation. Okay. UVB radiation stops your skin from frying, stops your DNA from mutating, stops you from getting cataracts in your eyes, and it's all around a very jolly good molecule to have up in the stratosphere. So, I will get used to this pencil one day. Of course, our driving reason is that it occurs everywhere in the IB syllabus. So, let's have a look. Ozone formation. You'll find many websites discussing ozone formation. What is basically what we need to know for IB purposes is we need to know that we have an oxygen molecule, which is this one here, which is going to dissociate into two oxygen radicals. Free radicals you'll be familiar with from your halogenation of alkanes. It's the same system, which is going to be, is it hetero or homolytic fission? You know, it's homolytic fission. One electron goes to each of the species, and the black dot I've just noticed is present. The little red dot, which is there, is not. There we go. So we've got two oxygen radicals. Free radicals are highly reactive species, as you know, and they will extinguish or react with another molecule as soon as they get in touch with it. So this is how we get oxygen into two free radicals. Those free radicals are then going to collide with an oxygen molecule, and we're going to make O3. So let's say hello to O3. It's the first time we've seen it as the molecule in this presentation. Here's our good friend ozone. We're going to spend the next half an hour or so talking about. We obviously care about ozone destruction, and the destruction follows a similar path. We have a photon of light coming in with E equals HV. It's the same photon here, E equals HV. Notice this is less than 242 nanometers. Notice for the destruction, it's longer wavelength, 200, or it's a longer wavelength, so 320 nanometers. That will become important later on when we do the calculation. So just bear that in mind for now. Okay. Shorter wavelength. What does shorter wavelength mean? Well, shorter wavelength is going to be higher energy, isn't it? So up here, this is a higher energy. High energy. I will work on my handwriting, promise. And this is lower energy needed to actually destroy the ozone. So ozone, we have O3 here going to an oxygen radical and an oxygen molecule. So it's bond breaking. bond breaking, putting energy in, so that's an endothermic process. We'll come to that in a second. And then the oxygen radical will combine with another ozone molecule. Instead of O dot plus O3, we now end up with 2O2. And the O2 is no good at protecting us from this harmful UVB radiation, which ozone has been doing a fantastic job at saving us from for a very, very long time. You probably all know why that job stopped being done, and we'll come to that later. So a question from a few years ago, which is why this is an important part of the presentation, and students were quite flummoxed by this because it was asked in a manner which was unusual. They said, which steps absorb UV light? And students were, well, how on earth do I know? I know the mechanism. I know that oxygen becomes two oxygen radicals. The oxygen radical combines with oxygen to make ozone. Most students remember 1 and 2. The majority of students will remember that the destruction, ozone going to an oxygen radical plus O2, they could work that out. And then the oxygen radical with ozone going to 2O2. It was precisely the same as what we were looking at here, just in a bit more elegant format. So it was one of those beautiful paper 1 questions, identify which steps. Was it step 1, step 2, step 3, step 4? Was it 1 and 3? Was it 1 and 2? Was it 2 and 4? Was it all of the above? We all know the type of question. The chilled students, let's call them the chilled students, they sat back and they thought, well, hang on a minute. So if oxygen is dissociating into 2 oxygen radicals, that is bond breaking. And I could take a pencil, I often do this in class, and break the pencil. I shan't break my Apple pen, that's not going to end well for this presentation. But it can break a pencil. I have to put energy in to break the pencil. So it's an endothermic process. So in essence, it wasn't a difficult question. It just looked difficult. If you see beyond, you see behind what they're asking, we're breaking an O double bond O, aren't we, to make 2 O dots. So that must be endo. Obviously this is exo, because now we're bond making. So if we're doing the energy profile, exothermic is going to be lower energy products than reactants. Forgive my graffiti drawing there. The next step, which is the first step in the destruction of ozone to give in a radical plus oxygen, that again is bond breaking, because we've got our O, 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 double single bond, we'll have some delocalization, and we'll save the discussion of that for the next slide. But looking at ozone bonding, we can work out that hopefully steps 1 and step 2 actually find ozone throughout the syllabus. But where does it first turn up? It first turns up in bonding, doesn't it? And now let's have a look at some structures that we may well be familiar with from the off. I'll give you a couple of rules. If you know the rules already, that's great. And this is what I teach to my kids. Sorry, I'm looking at the iPad and writing, so I'm not looking away. So we have bog standard oxygen. There it sits. There's O with its 2 lone pairs of electrons. The IB don't care if you do it as 2 dots. They don't care if you do it as 2 crosses. That's all the same thing. Okay, so this is, let's call this happy oxygen. That's happy oxygen. But what about if oxygen has 1 bond? Well, if oxygen has 1 bond, can we fit that into here? Yeah. Whenever oxygen has only 1 bond, it has 3 lone pairs of electrons, and it also has a formal negative charge. I say formal intentionally. It is the formal charge is going to be -1. The formal charge will be -1. We'll explore that shortly. And then what about this little tinker here? Well, that's not got 2 bonds, so this has got 2. This has got 1. This one here has got 3. So when oxygen has 3, that's a double, a single, and a lone pair. That's an unhappy oxygen. Okay, that oxygen is nowhere near back its friendly oxygen molecule you've been familiar with for a long time, and actually ends up with a formal charge of plus. Now, just to emphasize here, this is not plus like Na plus or Mg2 plus. It's not loss of electrons and then an imbalance of protons and electrons to give a +1, +2, +3 charge. It is the concept of formal charge, which is a set of rules that we use to track electrons. It's nothing more than accounting for our electrons in species as they go through a chemical reaction. So let's have a look at these. These are clearly resonance forms. We can call them hybrids, resonance hybrids. They used to be called, if you can come back, thank you, canonical forms, but I wouldn't worry about that. All that means is that I'm old and you're probably not, because you, you probably don't remember those there, so we don't need that one. Right. And what do we see? We see 1, 2, 3 lone pairs of electrons, formal negative charge, one dative covalent bond, DCB. Dative covalent bond. Do you remember what dative covalent bond is? Of course you do. A dative covalent bond is where both electrons in the bond come from one of the species only. Okay. Did we follow the rules? Yes, because we've got 1, 2, 3, 1, 2, 3 lone pairs of electrons, one bond, formal negative charge. So it's this one, 1, 2, 3, one bond, formal negative charge. This one has got 1, 2, 3, so that's 1, 2 double and third for the dative covalent bond and a lone pair, and it's an unhappy bunny in the +1 formal charge. And then this one here is a happy bunny. This is oxygen as we've known and loved it for a very long time. And there's the oxygen molecule, 2 lone pairs of electrons, 2 bonds. We know that has a formal charge of 0. What's the difference between this and this? Well, you could say that they are mirror images. I'm almost thinking of the word enantiomers, but I'd never use that if it's not an organic compound. They are mirror images. You are not wrong. You are quite right. However, the bond is jumping from one side to the other, and that jumping we represent by a formal full barbed arrow. These here, because it's a pair of electrons that's jumping. It's a pair of electrons, which is why it has a formal negative charge, formal negative charge, formal negative charge. Okay. Students made a mess of this a few years ago when they were asked to draw the resonance structures for ozone. And what a lot of students did was this. And they drew, they knew that one was minus, they knew the middle one was plus, and then they did the dotted lines. Okay, you will have seen that in class. I teach that in class as well. But this is the hybrid of the resonance structures. The question was for the resonance structures, not draw the single hybrid. Okay, draw the resonance structures. You must draw the extremes, the hybrids. So be very careful of the wording. That often does catch students out. Okay. Gavin, you're ahead of me in a minute. We'll come to that, my mate. So hopefully, just so you know, I'm drawing on an iPad. I'm watching on my broadcasting software and on YouTube, and I have my phone going as well. So if I take a little while to answer your questions, that's the reason why. Okay. Resonance forms, as I've just made the point, are here. This removes the charges just so that you can see it more elegantly, and hopefully you know now. If it says draw the resonance forms, you draw the extremes. I then started thinking, all right, the standard level, what do they need to know? Well, they probably need to know most of this. Okay, so the bond lengths are going to be identical due to delocalization. There does appear to be, well, there is at the extremes, a double bond here and a single bond here, and a double bond here and a single bond here. But this is reality, isn't it? The hybrid is reality. So here, thank you, Elise. Yep, here, this arrows, if these are the ones you're talking about, Elise, that is the movement of a full pair of electrons, because if it's a half barbed arrow with just one arrowhead, it's just one electron, like making a free radical in homolytic fission, but this is moving a pair of electrons, so it's actually reformed the bond. Is that okay, Elise? You got that? It's almost in real time. I think there's about a 5-second lag. Okay, I'll come back to that in a second. So the bond is, no really, the bond is going to be intermediate between a single, and when I looked in the data booklet, the single O to O bond, this one was 148 picometers, and O double bond O, as we know and love it, is 121 picometers. So it's going to be, well, the bond length, that's the bond length, is going to be intermediate between those two, isn't it? So there's 27 spots, 13, it's going to be about 135 picometers. The bond angle is going to do exactly the same. The mark scheme, I checked this, would accept anywhere between 110 and 119, but we do have 3 electron domains, right? We've got a lone pair, we've got a double bond, and a single bond. So we have 1, 2, 3 electron domains. So if there were no lone pairs, it would be 120 degrees. Let's keep with the green. But for every lone pair that we add, we reduce by 2.5 degrees, which would give 117.5. Thank you, Gavin. Thank you. Certainly the IB would accept anywhere in between, as long as it was greater than 121 and less than 148 on the mark scheme. All of that will be acceptable, including what you've just put, Gavin. Thank you very much for your comment there, mate. Yeah. So the bond strength of oxygen is clearly greater than the bond strength of ozone because it's a double bond, but ozone is 1.5. It has a bond order of 1.5. Oxygen has a bond order of 2. So the bond strength of oxygen is going to be higher than the bond strength of ozone. This is me just thinking of ways that IB could ask questions comparing the two. Ozone absorbs at a lower frequency and longer wavelengths than does oxygen, okay, which means it's really good at doing thank you, Gavin, for googling as we're going through the presentation. That's really good for us, for keeping us the UVB away from our skin and our eyes. Okay, so these are the things that I think they could potentially ask, certainly on a paper 1, maybe stretch on to a paper 2. Okay. This is definitely some higher level stuff here, because I'm sure the higher level students are thinking, well, what about the hybridization? There's always something about hybridization. And yes, the IB will definitely ask about hybridization. So we've got 1, 2, 3 electron domains here, 1, 2, 3 there, now 1, 2, 3, aha, we have 4 here. So that's 4, that's 3, that's 3. So the 4 will be sp3, and the 3 will be sp2. So again, I'm thinking they could give you these resonance structures, identify the hybridization at each oxygen. If that's not been asked yet, that would be a great question, IB. And of course, we have 1, 2, 3, 4 here, and 1, 2, 3 here, and 1, 2, 3 here. So again, that's just going to be the inverse of this one. Instead of sp2, sp2, sp3, it's sp3, sp2, sp2. So we're just counting them up. If you're not sure what I'm talking about there, I do have a video on hybridization. I suggest you have a look at that one. Okay. However, there are 2 equal resonance structures, and it's an average of the 2. So it's intermediate, and really they are all going to be sp2 hybridized, because in essence there are 3 electron domains around each of the oxygens. Again, IB, if you've not asked that question yet, that would be a great question to ask the higher level students. Draw the Lewis structures, identify the hybridization, and then they could ask you, couldn't they? I just thought of this. They could ask you, what's a sigma bond? What's a pi bond? And you're going, oh, it's that question again. Sigma bond and a pi bond. And you're thinking, I know this, you're not going to get me. And pi, we know that it's above and below. And we know that it's parallel. And if you try to draw it, it kind of looks like that when your teacher does it on the board, because their art is as terrible as mine. And the sigma bond is hybridized from S and P, and that's probably the worst sigma bond I've ever drawn in my life. But you get the idea, it's axial overlap. And you could talk about those bonds within ozone, as you could within any molecule. The IB love ozone. The other one that they love are nitrogen oxides. We're not going to go into those today, but maybe that could be a future video. Okay, so I had a look at the hybridization. We've had a look at the basic stuff on bond lengths, bond angles, resonance structures. So now let's move it on. Oh yes, I thought, what if they decided draw the hybrid orbitals? Could they ask you to do this? Maybe I'm stretching the point a little bit. Draw the hybridized orbitals. So here's the sigma bond framework of the sp2 equivalent hybridized oxygen atoms in ozone. And clearly I didn't draw this. I could never draw anything this neat. But we have the axial overlap of the hybridized orbitals. Don't forget sigma are hybridized. It's the pi orbitals that are unhybridized. And if it asks you to draw the hybridized, then you could draw the hybridized pi orbitals, which we start with the pz, and if we've got a triple bond, then we go back to the p1. Really see here, first of all, this is wonderfully artistically accurate, and we can see the interaction of pi electron density, which I normally scribble on the board like that when I'm teaching it. Gavin, thanks for your comments. Do you ever hint at the existence of molecular orbital theory when teaching hybridization? I have mentioned it, Gavin, and I think it's in the Pearson book. It's in one of the common textbooks. I have resisted going into it for fear of complicating it any more than is necessary, because it's not going to be asked on the paper. But I think it's a personal choice of teachers. If you choose to do that, then go for your life, knock yourself out. But this thing, formal charge, even in the staff room at school, I will mention formal charge, and people will look to the floor and go, "Oh no, not that thing! Please, not that thing!" And it's one of those things in IB chemistry, which is really straightforward, and because of that reason, people get it wrong. It's like the average bond enthalpies and breaking, takeaway, making, and they miss a 2 or a 3 from the equation, or they miss one of the bonds, or they forget to do the OH bond in an alcohol because it's drawn as OH in the question, that sort of thing. This is in that same realm of, why do people get it wrong? And why did I get it wrong, more importantly? When people look at it, why did I get it wrong? It was just so straightforward when I thought about it. So what do we care about? We care about the group number, don't we? And oxygen is always in group. Now this is old school now, isn't it? It's group 6, but we know it's group 16, but for formal charge it's quite an old concept. We still use group 6. Okay, so it's group 6. Now let's start on this end here, the blue one. This is nice because we've got 2, 4, half of 4 is 2, so that's 6. So it's 6 take away 6 is 0. I'll just do that again. It's in group 6. I know it's group 16. It's in group 6. There are 2 lone pairs, but there are 4 electrons in those lone pairs. And then we look at it used to be called the electrons that are associated with the atom. Okay, so I just look, I go, it's group 6, 1, 2, 3, 4, 5, 6. 6 take away 6 is 0. And I know I've seen probably 2 or 3 different ways of calculating formal charge on the internet, 2 of which confused the hell out of me. I had no idea what they were doing. But it's just accounting. You're just doing the accounting for the element. It will always be group 6, but now we've got how many electrons are associated with this central one. Well, there's 1, 2, 3, 4, 5, because there's only half. There's 2 electrons in one bond, but only half of them are associated with the atom that we care about. So now that's 6 take away 1, 2, 3, 4, 5. So that's the +1. So when I was drawing O3 ozone earlier, that's where the formal charge of +1 comes to. Okay, so how many are associated with it? This end one is group 6. They all were. They were group 6. And now I'm sure you're ahead of me. You're going, well, I can see, Mr. Midgley. 1, 2, 3, 4, 5, 6, 7. And 6 take away 7 is -1. So that's where the +1 and the -1 came from when we were looking at the resonance structures right at the beginning of this little presentation. So the +1 you can see is in the middle, which is up here. Let's go purple. We're not going to purple yet. So up here, +1, +1, and the -1 and the -1 That is the formal charge. And that comes from this little sequence of sums that you can see that I've done here. Now hopefully I'm going at a reasonable pace, but you can see what's going on. I will share this whole presentation as a bit.ly underneath the video at the end when I've got a minute, probably this evening. Okay, here's the money problem. This flawed many students. This was last year. Yeah, I think it was 2019. All it said was determine showing the wavelength in meters, oh, thanks for that, of ultraviolet light absorbed by a single molecule in one, I've missed out the word there, in one molecule of ozone. And students were like, what? What? It did say with using, I think, table 10 and 11 in the data booklet. And in table 10 and 11 of the data booklet are the bond energies for oxygen, O single bond O, and for O double bond O. So when the kids that got it right clearly did what I'm about to show you here, but OO is 144 and O double bond O is 498. And again, I've checked the mark scheme. The IB would allow you to calculate using any number. Well, they wanted it equidistant. I've gone for 350 just as a gamble, but as long as it was longer than the O double, higher energy than the O double bond O, or less energy than the 498, in that range there, and you put that into this calculation, then the IB were happy bunnies, because you had to show there's an intermediate in between. Was this SL? I think it was at least, yes. Yeah, because it's just E equals HV, which confusingly, dear IB, it's E equals HF if they do physics, bless them, thanks for that. Anyway, right, so we have a bond energy. Let's say I used 350. You could have used 300, you could have used 400, okay? It's 350,000 joules, 350 by 10 to the power 3, 10 to the power 3, joules per mole. Oh, I did that. So for a mole of our ozone, it's going to be 350,000 joules for 1 mole. And then the thinking students thought, well, that's for 1 mole, and this wants it for 1 ozone, and bond is even in inverted commas because the IB know it's intermediate between a single and a double. So you need to take that energy per mole and divide it by good old Avogadro's constant. Then you've got the energy of 1 bond. And that would have got you a mark. That would have got you 1 mark on the mark scheme. Reassuringly, this was a 2-mark question. A 2-mark question. Many students just think, I'll go do something else. So we found the energy for 1 bond, which I got to be 5.81 times 10 to the power of minus 19. Thank you to Mr. Gardner at our school for checking my calculations before I went live with this presentation. So E equals HF, and that means that F is C over lambda, so E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. So we need to rearrange for lambda. Oh, thanks, Kajal. At ease, Elise, at ease. Thank you, Kajal, for checking. So lambda is hc over E. H is in the data booklet, Planck's constant. C is in the data booklet, 3 times 10 to the 8. And my 5.81 by 10 to the minus 19, I worked out by dividing the energy for 1 mole by Avogadro's constant, given the energy for 1 bond. Plug the numbers in the calculator. Hopefully you agree. I got 3.4 by 10 to the minus 7. Gavin says, a nice demo by Chris Bishop. He explores a mixture of hydrogen and chlorine initiates. Oh, yes. Excellent idea, Gavin. Excellent. Love it. And we can compare that with our good friend oxygen, because oxygen we know is 498. And we'll plug the numbers in again. 498,000. Whoops, daisy. 498,000. Where did I go? Speed of light divided by the energy for 1 bond. And we've got 2.4 by 10 to the minus 7. So this is clearly longer wavelength, and oxygen is clearly shorter wavelength. And I think it's one of those things, when you know, but a lot of students just looked and went, nah, I'm going on to the next one. Okay, so per mole, 1 bond, Planck's speed of light divided by your answer for step 1, and you will come out with the wavelength to dissociate ozone and oxygen. Now they asked that last year, so it's unlikely to be asked this year, but any derivation or transposition of that, I'm sure, is fair game for future examinations. Okay, now ozone depletion by CFCs. Clearly you know my name is Mr. Midgley. My namesake was called Thomas Midgley. If you've read Bill Marshall's History of Nearly Everything, there's a whole chapter on this Thomas Midgley, and one of the things that he invented was CFCs, or chlorofluoric, at keeping things cool or cold, and they were fantastic propellants, and people pumped them into the atmosphere for far too many years, until technology kind of caught up and went, hang on a minute, when we look at our beautiful ozone layer, that thing's disappearing, particularly over the Antarctic, and even getting as far from the Antarctic as far south as Australia, certainly correlated with higher incidences of skin cancers. So what's happening here? At first look, it does look a little bit horrific. However, it's just the same as if you're doing yes, Gavin. Yes. If I can continue the story, just in case anybody's not heard this one, I'm sure most people have. He died. His manner of his death I found most amusing. He contracted polio, and he constructed a series of pulleys and ropes and weights to get him in and out of bed, because he was a creative chap. He also put lead in petrol, which is given lots of kids asthma. But one night he fell asleep, and I think he pulled the wrong lever on his bed contraption, and it wrapped itself around his neck and strangled him, and that was the end of old Thomas Midgley. But his namesake is right here, right now, having a go at teaching some chemistry. Yes, hoist by his own petard. Indeed. Anyway, Thomas Midgley's chemicals, here we are. I salute you, my namesake. And what's happening? It's one single there, so it's homolytic fission. The IB could ask you to, again, compare and contrast heterolytic and homolytic fission. Gosh, they'd love to do that. They will also ask, why didn't the CF bond, no worries, Elise. Why doesn't the CF bond break in response to UV radiation? Well, I can hear probably most of my class saying, well, Mr. Midgley, that CF bond is so strong, the electronegativity of fluorine is so high that it's going to be massively polarized. It's going to be so strong and held really tightly. And this bond's going to be shorter because this has got extra shell on the chlorine, so it's going to be further away. It's going to be easier to break that bond, and they would be absolutely right. So this is, what sort of step is this? This is an initiation step. Initiation. Why is it initiation? We've got a neutral molecule, and we've gone and we've made two radicals. Radicals, massively reactive species, can't wait to quench that little one electron. It's like the annoying cousin or the annoying sibling. It just needs to do something that's going to annoy you, and it does. Okay, here's our ozone. Remember the formal charge, 6, 2, 4, 6. So it's got 1, so it's -1. Remember all that? Of course you do. These are going to attack from a lone pair. It doesn't matter which one. The IB don't care. A lone pair on a terminal oxygen to the free radical here. That chlorine is going to rip that oxygen off here and leave us with O2. What's happened? Well, the story is we've gone from ozone to O2 by virtue of this chlorine radical. If this was initiation, what's happened here? We've now got a radical, it's basically neutral, going to a radical and a neutral. So this is a propagation step. It's propagating because it's going to go on, and oh look, there it is. That ClO radical here is going to react with another, and now we have radical plus radical, and now we've just made a neutral. So this is a termination step. Terminated the reaction. But did we? No. Cl2O2, that's unstable. It's not going to like that. Look at this. We've got the lone pairs of electrons on the oxygen, 3 lone pairs of electrons around each of the chlorine. It's just going to fall apart, and indeed it does. So here we have 1 electron going to each species. Again, it's homolytic fission, creating 2 radicals. Oh my gosh, we've got 2 radicals. What's going to happen? Well, that Cl dot is going to go right back where it came from, back to step 2. It's going to go up here, react with another ozone and make some more oxygen. Hence it is catalyzing the destruction of ozone, which was protecting us. And this was all because of someone called Mitchell. Yay. If you can hear a baby crying in the background, don't worry, she's been looked after. So our ClO2 radical here, what's going to happen to that beastie? Clearly it's unstable. Well, it's going to make some more oxygen, a chlorine radical, which will go back into here and keep the cycle going, destroying ozone as it goes. So, CFCs, not nice beasties to have up in our stratosphere. Thank you, Mr. Thomas Mitchell. The syllabus also mentions nitrogen oxides. I'm going to have to choose a funky coloured pen so you can see what I'm doing here. Can we have a white pen? Yes, we can. Will that work? Yee, bingo. Right, nitrogen monoxide. I did mention nitrogen oxides. The IB love these things as well. With ozone, it's going to make some NO2 and O2. The NO2 here is that one. There, it's going to react with O dot. Can't see that, it's an oxygen radical, making nitrogen monoxide and oxygen. Overall, because nitrogen dioxide is there, and it's there, and nitrogen monoxide is there, and it's there, so it cancels out. So we have O3 plus O dot, making 2O2. They don't mention in the syllabus that you need to know the intricate actual mechanism of that degradation. It just mentions that nitrogen oxides and CFCs will degrade oxygen back to ozone. I think that should be enough. They could ask you a higher level kinetics question and give you some rates. They could ask you, I don't know, establish the overall rate equation if they give you the rate determining step. I think I've given the IB enough ideas for questions already. So basically, what do I want you to take away from this? My white pen's not going to work anymore. Free radicals, CFCs, burning of fossil fuels, degrading the ozone layer. Creation, you should know UV plus O2 makes oxygen radicals, which then collide with oxygen to make ozone for the creation. How is it destroyed? Well, chlorine radicals can make oxygen gas, so O3 has gone to O2. How did they destroy the ozone layer? It's catalytic, because don't forget the Cl dot was regenerated at the bottom, that went back into step 2 to degrade the O3 back into O2. And here we go. What type of atom in a CFC molecule is most destructive? It's the chlorine, because that one is liberated most easily and is highly reactive, as all radicals are, so will destroy our ozone. Now, I do have some good news. So I did a bit of research, and it turns out, I think in 1986, was the Montreal Protocol. And you may be happy to learn, or you may be know this already. From the Montreal Protocol in 1986, there has been a 98% reduction in the production and use of chlorofluorocarbons on planet Earth. So shares in Mr. Midgley have gone down since the Montreal Protocol. Okay, they've gone down, but the ozone layer is by no means healing as quickly as we wanted. They suspect, projections, I got this from NASA, was that the polar ozone will be pretty much re-established by the middle of next century. So we're certainly beyond mine, yours, maybe your great-grandchildren's lifetime might see the resumption of a decent... Yes, Gavin, making me chuckle tonight. Agreed. I'm a northern boy, so I don't know if you're from the UK, mate, but I'm from Yorkshire, UK, and I agree with that entirely. I knew all the miners and stuff up there. Yeah. So anyway, it's declined by 98%, but the ozone layer hole is not repairing as much, and the Antarctic has been much later. Okay. So in terms of the syllabus, did we hit the syllabus? So this is all the syllabus statements from the IB. This is how much we love our ozone on the IB. So did we do the negative impacts of refrigeration and air conditioning? Come on, Apple Pen. Let's use a green. Let's use a fat nib. There we go. So negative impact of refrigeration and air conditioning use of CFCs has been, yes, I think we've done that. Bond strength in ozone relative to oxygen, yes. Again, it was asked last year, unlikely they're going to ask it this year. Moral, ethical, social, economic and environmental, wow, nature of science, ozone depletion and its causes. If you know that it was used in refrigeration, if you know it was used as coolant, I think you hit that box. Depletion of stratospheric ozone, catalytic action of CFCs, yep, we've done that. Polar regions, mentioned that, yep. The International Action and Cooperation, the Montreal Protocol, I think we've hit that. This is one of those still random factoids, I think. I hope it is anyway. Disinfection of water uses things like ozone to kill microbes. That was it. I'm not even sure that's in the core syllabus. It might be one of the option things. It doesn't ring a bell with me. How has ozone depletion changed over time? We touched on that with the next century and your great grandchildren. Might enjoy ozone coverage by the time they get to a ripe old age. Environmental cooperation, nature of science, peer review, you know all that. Wavelength of light, we did the calculations and mechanisms for CFCs and NOx. So when I went to the syllabus, Alt F, ozone, those were every syllabus statement that I could come up with. In making of this, I used the following references. Prof Davis is great. There's a university website which is good. NASA was brilliant. And huge thanks to Kajal Manglani, who was in this evening. Good evening, Kajal. Who shared a student web-based research activity, which I hope this video will sit alongside and complement both of those things as a great sort of hopefully learning experience for the kids. And then there's a chemistry of ozone worksheet which we put together at my school, I think that one. So we'll hit it, let's see what it does. I think that was at my school. And hopefully that's got the right sharing settings and you can use that. There we go. Okay. So hopefully you found that useful this evening, guys. It's been lovely to have you all along. And good evening from Singapore. And if there are any questions, feel free to put them in. I'm not saying I can answer them. I'll get back to you if I can't. But I'll stay on for a couple of minutes if you have any questions. Thank you very much for listening. Yeah, absolutely, Elise. The full presentation, the pages I will put underneath the video as a bit.ly. Probably give me an hour because I'm just going to have some dinner now, in all honesty. Cool. Thanks for your comments, Gavin. Been good to have you along, mate. Cool. Good stuff. Right, guys, signing off in Singapore. Have a great evening and look after yourselves. Stay safe. And thanks as always for watching. Please feel free to share. Appreciate the support. Comment, like, subscribe at the bottom, as they say. Thanks, guys.